meeting room, hein?
Oui, je suis en train de...
Good morning.
Hello. Good morning. Hello.
Hello.
Good morning, all. Can you hear us?
Hello, everybody.
Hello, Kela. Nice to see you.
Hi, nice
Can
to see you
everybody
too.
hear us?
Yes.
Yeah.
Okay. Thank you.
Let's go. Okay. So good morning, everyone, and welcome to the PhD defense of Sara Frusone. I'm Maxime Sermezan, a researcher at INRIA, and I will chair this PhD committee. In the jury, where we have so two reviewers, Riccardo Barbieri, who is professor at Politecnico di Milano, and Natasha De Groot, who is professor at Erasmus Medical Center. We also have Alexander Pablo Laguna, professor at Universidad de Zaragoza y Mecramase, professor at Universidad de Trento. As also part of people involved in the project, there are Axel Lowe, professor at Karlsruhe Institute of Technology, and Fabien Scola, who is cardiologist at the Nice University Hospital, and PhD supervisor, Vicente Sarsoso, professor at University of Nice Côte d'Azur. So Sarah, we listen to your presentation for 45 minutes.
Okay, can I start? Well, I am ready.
Yeah.
Okay. Good morning everyone, buongiorno tout le monde, buongiorno a tutti quanti. Prima di iniziare la presentazione di questo lavoro che riguarda gli ultimi 3 anni di questo percorso, vorrei spendere qualche parola nella mia lingua madre, l'italiano, per ringraziare in modo particolare le persone che sono venute qui oggi per me. Ensuite, je voudrais dire quelques mots en français, qui c'est la France est la langue, le français c'est la langue du pays qui m'a accueilli. Je tiens à remercier les institutions, les membres du jury, mon encadrant, les cardiologues. Then I will switch to English, which is the language of science. So today we are here to discuss my PhD thesis, explainable detection of spatiotemporal dispersion in multipolar intracardiac electrograms for patient-tailored catheter ablation of persistent atrial fibrillation. Atrial fibrillation affects predominantly the elderly population, is the most common arrhythmia, affecting 2 to 3% of population in general, and 10 to 12% of population over 65 years old. Today in Europe, we have around 11 million of people affected by atrial fibrillation, and we expect by 2060 to have 18 million. The incidence globally is around 60 million of people. And it's important to add that probably this is not a real number because many people do suffer from atrial fibrillation, but they are not diagnosed. But what is atrial fibrillation? Atrial fibrillation is a major cause of stroke. It's an irregular heart rhythm that leads to complication. This disorganized electrical propagation pathway is very dangerous and leads to an abnormal contraction of the atria. This means that the blood will not circulate normally, and we have an high risk of stroke and of blood clots, for example. The mechanism behind atrial fibrillation perpetuation are still incompletely understood. How to treat atrial fibrillation? Well, this is the last great frontier of cardiac electrophysiology. In fact, most common approaches to treat AF are medications like antiarrhythmic drugs, to slow down the beats, anticoagulants to reduce the blood clot risks. But they both have significant side effects in quality of life, they can lead to dementia, and they only alleviate the symptom without treating the original source of atrial fibrillation. In the past 25 years, atrial fibrillation understanding has evolved significantly. In 1918, Eisenhower identified the pulmonary veins as atrial fibrillation triggers. Later, Nadewani introduced the concept of complex fractionated atrial electrograms. Narayan will introduce later the concept of mapping rotors as possible triggers of atrial fibrillation. In 2017, Seitz will introduce spatiotemporal dispersion. The European Society of Cardiology in 2020 recommended the pulmonary vein isolation as the best treatment for atrial fibrillation, the golden rule. From 2022, with the increased use of artificial intelligence, some companies started to develop the first tools that allow personalized mapping and personalized ablation. In 2024, the European Society of Cardiology guidelines suggest that personalized ablation is the best option. By personalized ablation, we mean that we should not only treat the pulmonary vein, but we should look at the specific patient substrate. So how does catheter ablation, the best treatment for atrial fibrillation, works? Well, the cardiologist, thanks to the transfemoral venous access, under echography guidance, will introduce the catheter and will guide it up to the heart. Thanks to the use of the catheter, which is called the pentarray, it will record the electrical signal of the heart surface. This will result in the intracardiac EGM slits and also, combined with CT scan, in the 3D reconstruction. In this context, we can better have a look to the pentarray. The pentarray is composed by 5 branches. On each branch, there are 2 bipoles. From each of the 10 bipoles, there is 1 lead. We will call every signal lead, and the group of 10 leads simultaneously recorded sample. The result at the end of the procedure will be a map that in colors shows the electrical voltage. Catheter ablation is a minimally invasive intervention. Long-term and is the best one in terms of long-term success. This procedure improves quality of life with respect to medication, solving atrial fibrillation source directly. It is performed real time. The cardiologist will guide the catheter and will record the signals, supported by a big team, which is composed by anesthesiologists, nurses, radiologists, technicians of the software, for example. As we said, the pulmonary vein, to treat the area around the pulmonary vein, is considered the golden rule. Which are the problems? The problems are that this is not optimal, as we said, because studies show that there is a strong recurrence. So this means that patient will need to undergo a second intervention, redo. Additionally, once we used, so with the second catheter, radiofrequency energy to burn the cells responsible for the abnormal electrical activity, we cannot go back. This step is non-reversible. Once we burn the tissue, this means it will not conduct anymore the electricity, and this part will be isolated. Additionally, this procedure can lead to dangerous complications, because, for example, if we exceed with radiofrequency energy, the risk is to burn the surrounding tissue, for example, the esophagus, or even heart perforation. So, our question is how to establish novel patient-tailored approaches, because more and more patients are eligible for catheter ablation, but the optimal solution is still missing, and atrial fibrillation differs patient by patient, and PVI only, as we said, fails due to patient-specific mechanisms. So tailored approach are required. Well, a novel recent catheter ablation approach focused on spatio-temporal dispersion, also called STD, in electrograms. They are thought to be associated with active zone sustaining the arrhythmia. They are detected visually by the interventional cardiologist. So how does it work? Here we have a schematic view of the pentarray. We have the leads. Well, we consider those 2 points. So we will have to compare one bipole with all the bipole of the same branch and with all the bipole of the adjacent branches. then we have to look for shift in activation. By activation, with an abuse of notation, we will mention the peaks. So we have to check if peaks of contiguous lead are or not synchronized. In particular, we look for a time shift, which has to last at least the 70% of the atrial fibrillation cycle length, according to SAID's definition. Let's have a closer look. Here you can see that the shift is present. So it means that the cardiologist will burn the corresponding area. In the second part, the activation are perfectly synchronized. This is not spatiotemporal dispersion. So we said the cardiologist will ablate the dispersion area, so the green and the pink. Which is the challenge of that procedure? The tagging happens visually, real time at the block, thanks to the collaboration between the cardiologist and the Carto software. Signals are very difficult to interpret, and the interpretation happens visually. What we can do in order to facilitate this step? Well, recent advances in AI-guided ablation, like VX1 from Volta Medical, allow standardized identification of spatiotemporal dispersion, but they have some problems related to explainability, to transparency, and to interpretability, because the models used to train their algorithm are not available, they are black box, they are not the results are not reproducible because the data are proprietary of the company. So in the end, the most part of the scientific community decided lately to abandon this tool, also because in the latest study from 2025, they were able to show that it was better the manual ablation from the cardiologist with respect to the one guided by the software. So this is why lately. Okay, so what should we do? Well, let's summarize the main challenge. The main challenges for SCD identification are the following. There is a strong lack of consensus. So this procedure is subjective. Different cardiologists will tend to tag the areas differently. The data are sensitive, for example, to noise, to catheter movement. There are no public data set, and additionally, the available tools are not explainable. So we can divide our research problem in three main pillars. One, concerning the protocol. So try to standardize the definition and to move from qualitative evaluation to a quantitative approach. On the electrogram side, we need to solve the problems related to the labeling, because the data are labeled real time at the block during the intervention, thanks to the communication between the cardiologist and the carto engineer. And additionally, the signal quality, because the catheter has to be stable and well positioned while we record. Finally, on the method side, if we use AI, there is an explainability problem. So when I started the PhD, I tried to better understand the spatiotemporal definition. Discussing with the cardiologist and looking into the data, I understood that the SAID's definition does not fully correspond to what is done in practice. For example, in the case of SAID's, they mention at least the 70% of the atrial fibrillation cycle length in terms of shift. What cardiologists actually do is looking for at least a shift which has to be more than half of the atrial fibrillation cycle length, which to me is more than 50, not more than 70. Additionally, also the concept of adjacent leads that we mentioned before. So another important point concerns the activation detection within the atrial fibrillation cycles. So by local activation time, we should consider the timing of significant deflection. But what cardiologists really look at are the peaks, because if we look in the deflection band, you can see that it's very difficult because it's very fragmented. So it's much easier for them to look at the peak. So with an abuse of notation in the thesis, we will refer to the peaks and to the LAT without a distinction. So for us, it will be the same. Also because the shift is very small in terms of millisecond, and we have a bit of flexibility with respect to the spatiotemporal dispersion definition. Now I explain to you what spatiotemporal dispersion is. Let's play a little bit. So this is the real-time situation that the cardiologist has to face while he is labeling. You can see the time is scrolling and he has to look at the activation. Every recording will be 2.5 seconds. Are you able to guess if this sample is STD or not? Well, I will answer for you. This is not an STD because the activation are synchronized. Let's try again. Are you able this time? So let's have always a look at the peaks. We can see that sometimes a peak is at the center even with respect to the peaks of the previous lead. So in this case, in those leads, we have STD. Let's do it again, just to be sure we understood. This is STD again, but I want to show you how difficult it is. Imagine that they have this continuous scrolling. Now we are only looking at 2.5 seconds. They will have to do that for 3 hours. So, and finally, again, this is a non-STD sample because the peaks are synchronized. But it's not that simple. In fact, what I show you was the standard definition. Discussing with the cardiologist and having a look in the data, we understood that there are also sub-cases not included in the definition. In fact, one of them is what we call the intermittent activation. The dispersion in time can be also less than 50%, but can switch on and off at least in half of the signal. And this is what you will observe in the last leads. Another example, so this was STD. Another example, this one is the standard definition. You have tagged the last leads. This is STD. And this is another tricky one, the gradient activation. It means that across cycles going on in time, the dispersion can increase gradually up to the 50%. So all those sub-examples were not mentioned in the definition. So real data have a lot of challenges. Noise, unstable movement, they are also very unbalanced because there are a lot of non-STD samples and a few STD samples. Additionally, we were collaborating only with one hospital, the one in Nice. So it's not a multi-center study. The first data set that we had was called the raw data set. This data set has some problem related to the to mislabeling, to noise, to recordings which are capturing just catheter movement, instability. So what we can solve is the labeling. So we can ask the cardiologist to go again across the data offline after the intervention and to check if he is happy with the labels he added or if there was a misunderstanding between him and the software engineer. So the relabeling will lead us to obtain what we call the curated dataset. The curated dataset is a small subsample of the raw dataset. Here it comes another challenge, the online versus the offline labeling. So on one side, we have what we saw before, what we see when we try to label the 2.5 seconds. On the other one, we have the real life at the block. So the cardiologist is here and the technicians are there. So you can see there is a lot of space. Also, the stream of the data is continuous. They know who the patient is. They know in which location of the heart they are. Maybe they will be stricter on labeling sometimes, while all this information is not available offline. So what else we can do? We said that we can improve the errors related to labeling, but this is complicated because cardiologists do not have time to relabel huge amount of data. And discussing with the cardiologist and with the carto engineer, we discovered that in the carto software, it's possible to change some parameters related to the acquisition of the signals. Those two parameters are TPI, tissue proximity index, and stability. While in the standard setup, the TPI was off, now we switch it on, stability was 0.5, now will be 0.3. So I don't have the formula of stability and TPI because they are proprietary measure of the software, but we can try to understand what they mean. They are related to the location of the catheter, to the contact, and to the movement. So when we are restricted on those parameters, the software will acquire less data, but better quality. Additionally, I want you to remark that we cannot filter once the data have been recorded. So we have to set these a priori. Those are the data set that we obtain, the raw decorated, which is a subsample of the raw, the TPI, which has been acquired with different parameters. And in all cases, we can see that the fraction between the number of STD and non-STD indicates that this problem is highly unbalanced. We still do not have enough data. So in particular, there are some time delays. So we need to wait for the hospital to have the patients, for the cardiologist to do new recording. So while I was waiting for the TPI dataset, I started some synthetic simulation. So I used the OpenCard software and its examples to create what was called the rotor dataset. So a rotor is a mechanism of re-entrar activity. The circuit size is determined by the wavelength, and it has a spiral wave re-entry, characterized by a central core around which the activation wavefront rotates. So we consider the rotor hypothesis. We simulate some synthetic tissue patches where, using Kurteman's ionic model, we have cell healthy, scar tissue, and so the conduction of the tissue is different. This is a patch, two-dimensional, that has real-life dimension, so it's around 7 by 7, and we will simulate the electrical propagation, the healthy propagation, and also the rotor related to AF and to STD. Then we will simulate the pentaray catheter, and so we will record the simulated signals with the simulated catheter. What we obtain are synthetic data for STD. This is a non-STD, this is an STD, you can see the shift. Now, we want to try to use some machine learning techniques to see if it's possible to automatically classify the data. So we train, test, validate, we pick 11 different methods of machine learning, we pick some CNN, and we also do some hyperparameter tuning to improve the performance. We create 3 different settings. One, training on the raw, testing on the curated. One, training on synthetic, testing on synthetic, and another one, training on synthetic and testing on curated. We report the best performance for every configuration across all the 11 methods that we applied. You can see that it doesn't matter the training set, the results are always very poor. If we opt for CNN, it doesn't change much, except for the synthetic scenario. What we can get from that is that probably the synthetic data is too simplistic with respect to the real nature of the AGMs. Additionally, there might be too many problems related to the real data set. So too much noise and too much ambiguous samples. So what can we do? Well, we can try to switch from an AI approach to a signal processing approach. Why? Because when we use signal processing, we don't need training. So we don't have to use a huge amount of data, which was a problem before, because the curated data set is very small. We are flexible with respect to changes in the procedure or in the labeling criteria, and we have a higher explainability. Once we failed with machine learning, with the machine learning approach, I went back to the block. I was looking again at the intervention in order to understand how to solve this challenge. And so we decided to switch from AI to signal processing, to go back to traditional approach. How? we propose a novel signal processing pipeline. It's an alternative to AI. It's a mathematical pipeline that eliminates data dependence because you use data only for testing, and reproduce the decision-making process applied by the cardiologist. So we have the 10 lead, we have the group of comparison according to the different branches of the pentarray, we extract the local activation, and then what we do is we compute the time shift between local activation. And finally, if we face one of the examples I explained you before, we will be able to classify STD or non-STD. As we said, the signal processing approach has a lot of benefit thanks to the explainable criteria and to the modular architecture and the no training. But when we try to go for this approach, another challenge comes, the peak detection. So those signals are very noisy. Signal characteristic can vary a lot, and additionally, there is a lot of expert disagreement also for the peak labeling. It's even impossible sometimes where signals are very fragmented to understand where is the peak. Finally, another problem will be also matching the detected peak among leads, so understand which one should be compared. So it's not very easy. How to solve that? We go to the literature. There are a lot of methods in signal processing for ECG peak detection. There are energy-based methods. There are what we call software style, so the admin of the derivative. And we also propose an adaptation of the methods for ECG and a novel peak detector. Additionally, we want again to try with some machine learning techniques. Something we can already cut off is the thresholding approach. Why? Because as you can appreciate here, the scale can change really a lot. For example, there, it can arrive up to 2. Here is 0.1. So also very small amplitude signals can be interesting, can show spatiotemporal dispersion. In fact, it is important not to discard them, so we cannot use a simple thresholding approach. So I list quite fast the different state-of-the-art methods that we imported from ECG, but there is another problem. So ECG and EGM have different nature. ECG methods cannot be directly applied to EGM. In fact, ECG capture the global cardiac activity, EGM reflect the local one. EGM show fractionated and double potential. The activation have shorter duration, variable amplitude, and while in ECG the noise has some characteristics, in EGM is not the same. It's more related to the catheter instability and far-field inference. So we adapted the Pantomkin method, normally used in signal processing for peak detection, changing the parameters empirically to reflect the spectral and the temporal characteristics of EGMs. Higher frequency passband to retain sharp deflection, shorter MVI to preserve temporal resolution, and a reduced refractory period to accommodate closely spaced events. We reproduced the Carto style method, which takes the derivative, the inverted derivative, the nonlinear energy operator that enhances sharp deflection in EGMs, and support automated and robust LUT extraction. And we try to choose which machine learning techniques to use. So regression or classification. This is a regression problem because if we opt for classification, it's too unbalanced. It's 2.5 seconds and just a few peaks. So again, we try different methods in machine learning, like linear regression, the season 3, SPR. We need to accommodate a tolerance window because we are not interested in a millisecond precision. We need to match when we check the K performance indicators, the predicted with respect to the real ground truth. And so we need to create a custom loss. This for the machine learning approach. And then we have our proposed peak detector. The proposed peak detector will break the leads in 162 milliseconds, which is the average atrial fibrillation cycle length, find local maximum per cycle, so relevant peaks will be considered as local activations. Again, another challenge. In real data, we don't have a labeling for the peaks. So how can we check that our peak detection is correct? We generate another synthetic data set thanks to the collaboration with the KIT. We reproduce again the wavefront, the spiral wave dynamics sustained by a fibrotic ellipse, and several pathological modifications in the Carte-Manche model. This model is much more accurate with respect to the first that we used, thanks to the collaboration with the expert of biomedical modeling. We obtain transmembrane voltage and AGMs. There is a temporal alignment between the two of them. If we have a closer look, we can see that while in the transmembrane voltage, the peak is quite sharp, it's much harder to see it in the AGM. So we used the transmembrane voltage to detect with the simple thresholding method the ground truth of the peaks. We shifted a little bit of 3 milliseconds or 4 milliseconds, and we consider that as ground truth for the peak. Minor shifts occur due to the physiological and technical variations of the model. Then we have to match cycle by cycle correspondence, both when we check the peaks and also then when we will look for spatiotemporal dispersion. What is the result of the peak detection in the synthetic scenario where we do have the ground truth? Here it is. So we have nonlinear energy operator, adapter Pan-Thompson, propose, decision tree, ADA boost. The Carto is the software one, and then all the other ACG methods that haven't been adapted except for a few parameters. So I will obscure them because they are not very interesting. We keep the best performing method that are able actually to classify correctly almost all the peaks. And we also do some Monte Carlo simulation, randomly perturbing the signals and repeating the detection to evaluate stability with respect to noise. We can see in this case that the metric, even with the high SNR, is still quite good in detecting the peaks. The applicability in clinical practice is related, again, as we said, to the fact that most of the literature method contain some manual thresholding. They contain some filtering that needs to be adapted to the signal. In particular, what it's important to notice is that sometimes a single signal can have a high amplitude in some part and then have a very small amplitude in the other one. It's not the case of this one, but sometimes you can see that it varies from 2 to -2 on half, and then it varies from 0.5 to 0.5 in the other part. So the filtering will be affected. Same for an adaptive thresholding. Now we want to apply the peak detection on the real data, but we do not have the ground truth. So what we can do is just to evaluate qualitatively the peak detection, but we can use as a surrogate accuracy measure the final STD classification, which is based on the peak detection step. An important step will be a filtering with the sinus that is able in real AGM to enhance the sharp peaks. This is the result. Let's have a closer look. We can see that our method, the proposed one, so that uses the windows and the filtering, is able to detect the most prominent peak. This can serve as a reference for the cardiologist to understand where is the lat. While other methods on the real data, again, we need to evaluate these qualitatively because we do not have the ground truth, fail. Let's have a look to the best performing method. We have the signal, we have the proposed in blue, the adapted Pan-Tompkin in green, the Cartostyle in orange, and the NLEO in red. I can show you another lead. You can see that the proposed is always capturing precisely the most prominent peak with respect to the others. Now we apply the peak detection step in the pipeline, and we see that we obtain an F1 score for spatio-temporal dispersion classification of 0.65, which is an improvement with respect to what we obtained when we were training on the synthetic and testing on the curated, or when we were training with machine learning on the raw and testing on the curated. So we eliminate the we eliminate a step of the training, and we do not have this problem anymore. But we understand that timing alone is not enough. There was another important feature in those signals that we haven't faced yet. It's fragmentation. Fragmentation is used to quantify local conduction complexity. Currently, fragmentation is again evaluated qualitatively. So we want to switch from a qualitative approach to a quantitative one. Additionally, we want to test sales hypothesis that states that the degree of fragmentation of EGMs, time series, is not related to spatiotemporal dispersion pattern in patients with persistent atrial fibrillation. What we will do will be, we quantify fragmentation, we classify fragmentation automatically, and we compute fragmentation versus STD. And finally, we ask the cardiologist to manually label fragmentation in some samples. Again, we start from the state of the art. We take some measure for fragmentation by Schilling et al., like the number of active segments, the activity ratio, and there exists also software-based metrics, but in our case, they were not available. We proposed some new fragmentation indices that quantify the level of uncertainty or randomness within a probability distribution in the case of the Shannon entropy, for example, the normalized variance, the normalized median absolute deviation, the percentage of alternating segment, the zero crossing, and finally the dominant frequency that we already know is not really related to fragmentation, but for the cardiologist it was interesting to test it with respect to STD. So we can evaluate fragmentation on the real curated dataset. We can evaluate fragmentation on the TPI dataset, which is less fragmented by its nature, and where the cardiologist labeled visually fragmentation. And also we create a simplistic synthetic dataset for fragmentation. This dataset is not coming from any biophysical model, it's simply signals, where we simulate for 5 different classes of fragmentation. This is the case of the synthetic one, where each signal has the duration as it is for the real one, the frequency of 1000 Hertz, mimicking the real data analyzed in this phases, and we create some bursts and some clusters that are randomly computed in order to create the signals. Each burst is a sinusoidal waveform with frequency randomly chosen. Let's have a closer look for you to appreciate the gradient of the fragmentation shift. Here it is. And then we compute on those the Schilling metrics for fragmentation on those synthetic signals and the proposed methods. We can see that in the case of Schilling, 0 was the less fragmented for the most fragmented. Local max alternating segments capture a little bit it's decreasing, while in the case of the proposed methods, there are many of them that are able to capture the increasing or the inverted increasing level of fragmentation across signals. Inspired by Schilling et al. That tested some decision tree to see if it was possible to use the fragmentation metrics as features to predict the fragmentation class, we tested the proposed feature, the Schilling, and the combination. We can see that when we use the proposed, we get a very strong F1 score, on the prediction of the correct fragmentation class. The cardiologist label also the samples with respect to fragmentation from 0 to 10. Again, I want you to appreciate the gradient of the fragmentation from 0 to 4. This is like the global shape, and then from 5 to 10. You can see it's increasing. This is the TPI data set, and I appreciate the fact that you can see a lot of signals are not very fragmented, and this respects our hypothesis and our objective of changing the cardio parameters to create a data set which was not fragmented because of noise, catheter movement, instability, but which was fragmented for biophysical characteristic. We then compute the indices for all the classes. And so you can see how some of them reflect a little bit the fragmentation increase or decrease. And we also tried to plot the principal components across all class, but we see that the classes are very superposed. Also, another problem is that we have really a few samples, as we saw before, especially for some classes. This is why we tested some clustering algorithms to see if it was possible to incorporate some of the classes. So again, we try to automatically classify fragmentation using class aggregation, because there are some classes which are not big enough to perform machine learning. We use decision tree because we are not interested in machine learning optimization, and we use correlation analysis to decide how to combine the different classes. Okay. Here we test the correlation for the different indices with respect to the manual label of the cardiologist. And then we merge the classes. So we make low, medium, and high, merging 0, 2, 3, 6, 7, 10. The result will be an accuracy of 0.72 for the classification, where MAD emerged as the most influential index, so the most relevant feature for the prediction of the classes. We also go back to the curated data set, because we want, as we said, to understand if the state's hypothesis is correct or not. So if the level of fragmentation varies or not with respect to the STD, non-STD class. In this case, we do not have the labeling of the cardiologist for fragmentation, but we can compute the proposed metrics, and you can see that it doesn't matter the class, so STD or non-STD, the level of fragmentation, no matter the index, will be more or less the same. So we can confirm the state's hypothesis. So what have we seen today? On the protocol side, we were able to provide new spatiotemporal dispersion definition. So we go deeper in the understanding of the protocol, which in the end is very important because cardiologists need to agree. We develop some quantitative fragmentation metrics that are easy to use, that do not need any thresholding, do not need to be settled by hands, that they are automatically computed on the signals. On the data side, we did some synthetic simulations. As you were able to see, we created the rotor data set, we created the peak data set, and also the synthetic data set for fragmentation. In parallel, we worked on the acquisition of real data concerning the TPI data set, where we changed the parameter software acquisition, and we were able to improve the data quality. On the method side, we develop a peak detection algorithm and a signal processing pipeline to automatically classify STD. If I should summarize in one word, which is the major limitation of this study, the answer is the data. The data, because it takes time to acquire them, It's also difficult to agree on the parameters, to remind the technician to set the parameters in a certain way. The data that were available at the beginning were really very noisy. Some samples were even difficult for the cardiologist because they were a bit ambiguous with respect to STD, non-STD. There was a lot of fragmentation, instability. So the data are the most difficult part. There are no available public data set. Again, this is another challenge concerning reproducibility, for example, and the comparison with existing tools. If we would like to think about other possible technique, we have adaptive direction activation algorithm, ADA, which is a promising method for the detection of activation using correlation and morphology-aware processing to estimate the local activation. Another interesting point is to import what Sensoy et al. Did on the NIST dataset, so using evidential deep learning to quantify classification uncertainty, supporting more reliable and interpretable decision making. In his case, he changed some part of the neural network in order to be able not only to provide a prediction, but also to provide a parameter of uncertainty on the prediction, because we also risk sometimes the machine learning prediction is correct just by chance because it was overfitting one of the two classes, while providing this additional parameter help us to avoid so. And finally, I want to thank you for your attention, and I'm open to questions.
Thank you. Thank you for the presentation. So we'll go through the questions of the jury, starting from the reviewers and traditionally from the furthest away. So for you, Professor Natasha de Groot from Erasmus.
Yes, thank you very much. So how long do I have for the questions?
No strong limit on this. I think there's a big jury, so you're probably got a time limit, but
10 minutes?
between 10 and 15 minutes, up to you.
Okay. Well, then I'll start. So I would like to start with congratulating you and your entire promotion team with finalizing your thesis. I really enjoyed it reading. I was looking forward to today to discuss it with you. So first I will start with a few global questions. Now taking a look back at your thesis, which aspect of your thesis do you think was most innovative?
Most, sorry?
Most innovative.
Innovative, okay. Thanks for your question. So for me, I think the most innovative part was to try to quantify what for you, the cardiologist, is very qualitative. In fact, I come from a very theoretical background because I am a mathematician. So for me, it was difficult to understand sometimes from the description what the cardiologist was trying to mention to me. I believe that also in order to optimize something, we should have a problem with some numbers, some hypotheses, some tests. So this effort to give metrics and give numbers to the different qualitative approaches, to me, can be innovative, because thanks to that now you are really able to take a sort of meter and put it on the signals, for example, concerning fragmentation. Yeah. Additionally, another aspect that I think is very relevant is the fact that I try to focus not only on what was useful from an understanding and scientific point of view, but also on what was useful for a cardiologist that in a very far stage will use what we developed. For example, I know that can be annoying for you to remember every time to set some parameters, to set thresholding, to tick something in the software, because for example, if you forget, then the software measure will be wrong because we didn't set it properly. This is why the innovative aspect is also focuses on something which facilitates the user experience.
Yeah, okay, thank you for this elaborate answer. So a more specific question. On page 2 of your thesis, you write, a novel, promising, patient-tailored catheter ablation treatment focuses on localizing spatial temporal dispersion patterns in EGMs. But what do you actually think? So you've given a very nice description of these STDs, but how does it relate to the mechanism of AF? What are we actually looking at?
Okay, so STD are related to an abnormal electrical activity. So the electrical activity is not synchronized. One of the hypotheses related to the STD is the fact that there are rotors, as we state for the synthetic simulations. So it's important to detect STD because they are related to the rotors, which are triggers and instruments that maintain the atrial fibrillation. So this is why if we not only focus on the pulmonary vein, and we also focus on those triggering points, we are able to improve the final outcome. And this has been demonstrated by the study of SAIDS and other of his peers.
So you actually state that, if I understand you correctly, that the areas of spatial temporal dispersion, in your opinion, are related to the presence of rotors. Is that what you say? Yeah. But then there are also a lot of nice activation map technologies which has been introduced. Why not just simply making an activation map and looking for those rotors? Why would we then go so difficult and look at the electrogram morphology? What do you think of the advantages and disadvantages of these two approaches?
Okay, in this case, the data available were electrograms, and the spatiotemporal dispersion definition is related to the electrograms. This is why we focused on detecting it on the electrograms. So yes, if we consider the other approach, it's also possible to do it, but in this case, we wanted to focus on the signals, and so we look at the activation, etc.
Yeah. So you choose to look at the signals, and you have done a very nice job on analyzing the fractionated potentials. And then you say on page 71, pathological EGM, so fractionated electrograms, low voltage areas, and cafes serve as a direct electrophysiological marker of the underlying atrial remodeling. Well, I think this is an interesting remark because in your opinion, what are the causes of fractionation?
The causes of fractionation, again, it's a tricky point because for sure fractionation can also be another result of the rotors. So what the cardiologist does in this is that the procedure will be pulmonary vein isolation, spatiotemporal dispersion, and also burning areas related to fractionation, because also those cases can be related to rotors.
Yeah, but then what exactly causes fractionation? And the reason why I ask is that you mentioned somewhere in your text that you think it's pathological. Is then fractionation always pathological, or can it also be functional in nature? And if so, what could be an example?
The fractionation can be, yes, pathological or functional related to atrial remodeling, for example.
Yeah, are there perhaps also other causes of fractionation?
So other type of fractionation can be related to the surrounding environment, for example, the instrument movement. So we need always to distinguish the fractionation really related to the pathological or the remodeling part, and the fractionation related to poor contact or instability.
Yeah, so you have the technical reasons, you have the structural reasons, and then you have functional reasons. But even, for example, if you go up to a high rate where you have in sinus rhythm a normal potential, you can have fractionation just because you go into the refractory period. And also, if you have branching, for example, at the crista terminalis region, you just have during normal sinus rhythm already fractionation. So how can you discriminate these different type of electrogram fractionation with your approach? Maxime, you interrupt me if it takes too long.
So in this thesis, we didn't focus on distinguishing the different type of fractionation. We just focused on trying to quantify it. So we see that there is fractionation and we give a numerical quantifier. We haven't distinguished the different types also because no labeling for fractionation was available. We just got a numerical quantifier which was corresponding to how much fractionation there is in the signal, but not to the type of fractionation. I don't know if I've been clear.
Yes, you have been clear. Thank you.
Okay.
If I have time for another question, I'll look at the chair. Yeah, I have time. Okay.
Yeah.
On page 76, you provide a definition for STD, and you say you use here the criteria of 50% instead of 70%, but we know from high resolution mapping data that if you have a long line of conduction block, you also have spatial temporal dispersion. And if we take a look at the figure that's on that page, you see that there is indeed a time gap, there's fractionation, but the fractionation you also get when you have turning of a wavefront caused by the line of conduction block. So how do you discriminate that it's an STD caused by a long line of conduction block, where you can easily have also covering 50% of your cycle length, or that it's STD due to the presence of a rotor?
We do not distinguish that again. We only have the labeling for spatial temporal dispersion. There were some very minor cases where the cardiologist also had a small comment, but from the data side, it was not possible to distinguish for me.
Yeah.
So
Okay.
again, we consider STD as a unique group. We consider separately fractionation, and then we asked ourselves, should we converge the two of them? According to Seit's hypothesis, they were unrelated. We confirmed that, and so we do not include the fractionation measure in the SP pipeline.
Okay, I return the word to the chair by now.
Okay.
Okay,
Thank you for your questions.
Thank
So
you.
we can move to the next reviewer, who is Professor Riccardo Barbieri.
Yes, hi. Can you hear me?
Yes.
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 Okay. So first of all, congratulations. It's a very nice work. I really appreciated the structure of the thesis, very clear, setting up the stage and then up to the end. Really, you wrap it up very, very compellingly. So congratulations for that. I appreciated also the applications, the methods that you used, in particular the value of the signal processing in a world that now uses AI everywhere. So I really appreciated that part as well. So I mean, I liked so much the thesis that my surprise was the publication record. So I can't avoid asking you the question, how come I see only publications in conference proceedings and not a nice publication in a nice journal that could wrap up your innovations?
So this was due maybe to, so it was in the objectives that we had, but then due to timing, etc., we focused on writing the manuscript, and we said then out of the chapters, we will select the most relevant information and we will try to write a journal together. So it will be something that we will do probably in January in my free time, because I will be finishing the time allocated to the thesis in December, but I will put the best effort I can in order to do that, because I agree with you, it's a pity.
Okay, so I mean, it's in the making. A big manuscript is in the making. Okay, where do you think you're going to submit it? In a more clinical journal or in a more methodological journal? So what's your directions now?
My direction is for the signal processing pipeline, more signal processing related journals, while for the work on fragmentation, as we add these, let's say the work on fragmentation arises from a discussion with the cardiologist. So maybe in this case, as he also engaged himself in the relabeling, the offline labeling of fragmentation in the data set, I think in this case it would be interesting to go for something more clinical and to emphasize the correlation and the capability of the metrics that we developed to encode what is the clinical meaning of fragmentation. So my idea is that there will be one more on signal processing and another one more oriented to the clinical work, but we will discuss this deeper after I think we are done with the thesis, PhD defense, etc.
So given your background, very technical background from mathematics, how was your approach in dealing with the clinical world? How was your relationship along your PhD with the cardiologist? And then, so just tell me a little bit the story. But then, I'm really curious because I don't see that in the thesis. What are the plans for really bringing these algorithms in the clinical world, inside the operating room, and inside really make it fruitful from the clinician point of view?
So concerning my relationship with the cardiologist, for me, this was the most important part of the thesis. I remember when I was attending in mathematics, one of my first classes in statistics, my old professor told us the importance of discussing with the data expert, because as mathematicians, we only look at numbers. We do not know what's behind numbers. So the risk is that numbers can also tell us something wrong. So after what I learned during my bachelor, as I arrived, I said, I need to understand the intervention. I need to see it. So thanks to Fabienne, which was very kind and open for me to go in the room. I went at the block, I attended the intervention, I asked questions, I looked at all the steps that they perform. Additionally, always on the clinical side, one of the very hard part was that I extracted the data from the Carto software in the block. So again, I had to collaborate and to ask to the Carto software specialist also how to unzip all the folders that are contained in the Carto, because there is some documentation, but it's not very clear with respect to the real data structure. So for me, if I developed the mathematical pipeline was really thanks to my understanding of the practice that I had going in the room and being there while the intervention was performed, because offline reading papers, watching videos, it was not the same. There are a lot of details that you can only get if you are in the room, if you look, and if you ask. Additionally, this, let's say, trial-error approach was also very helpful, because we started with some hypotheses, and then I always try to adjust my idea with respect to what was in the data, to also the data availability that, as I said, was one of the biggest challenges. And again, on that point, I attach myself to your second question. So how do we use what we developed in the thesis? Well, this is not a multi-center study. So before expanding what we did, we should involve someone else with other data that maybe applies also a procedure which is a little bit different with respect to the one from Dr. Scuora. And once we validate on different data, then we can see if it's possible to incorporate in the medical software. An advantage might be that with respect to machine learning that we know, especially in the EGM domain, what happens is that sometimes there are centers that produce their models, they work great on their data set, and then you change the data set and it doesn't work at all. In this case, thanks to the flexibility of the pipeline, we can still arrange some changes on the different criteria. So it will be easier to adapt it to different procedures. But I see also, so I see the use of what we develop in the medical practice as something that should involve computational test, because everything was quite fast from a computational point of view, but real time we need to be very, very fast. And so other centers and other cardiologists that can test our methods and our results with respect to their data. Did I forget something, or I answered?
No, very clear. But now to be more specific, like to give a real case, no? How do you really envision practically, and if you have discussed with the doctors, I mean, the doctor will enter the OR, how it's gonna interact with your programs? How they're gonna communicate? Is it just a recommendation? Is gonna pop up and tell the doctor something? Really, how do you envision your?
So, okay, can I go?
Yes.
Okay, so I think that for example, the Carto software is something that is built to be personalized according to the cardiologist need. So for example, the fragmentation measure is something that it's already in the software. It's something that you can add and that can pop up. But the problem is that the measure they provide has problems, as we said, related to the fact that they do thresholding, filtering, you need to fix some parameters. So in my case, you would only need to tick this feature and it will appear on your screen. This is my feeling. The same concerning the peak detection. So I see it as support decision tool that can make the cardiologist's life faster and easier, because he has already a guidance that he can consider as a starting point for his decision and for the following steps of the intervention. Concerning so the STD identification, again, I think it can be something that pop-ups in the signal. So there can be, for example, an arrow showing you this is STD, but in this case, I believe it's also very important to add some confidence metrics in order to say how much we can trust this prediction somehow. So consider also if we fit in one of the criteria very well, or if we fit but not so much, so it's very important to be precise. And then I imagine this as something that we need to adjust, working in progress and listening to the cardiologist comment, because in the end they are the final users. But this was one last remark, maybe. This was something that we already took into account, because when I was building things, I was always asking to the cardiologist, what would you need? What would you like to see that you don't see now in the Carto? And he told me, this doesn't work. This you see there is, but if you don't take time to push all the buttons, it's wrong. I never read that number. So I think we should avoid this.
Okay, thank you. Do we have time for another question? One more question?
Yes.
So, I mean, the link between fractionation and STD is weak in a way, no, from your results. How do you see now proceeding in? I mean, do you believe that you haven't found the link that you wanted, or what do you think it's going to happen in the next study, either if you are taking it or someone else? What would you do to understand better this link?
I think I would get more data with fragmentation labeling, because the data that they labeled with fragmentation was very small, and it was the TPI data set, while the data where there was the labeling concerning STD, it was the curated data set. So we should create somehow a very big data set where signals are acquired with the novel setup of the machine, so that we don't obtain the fragmentation related to the environment, as we said, and then we can compare again, and we can also ask the cardiologist to label more samples, because there were some classes where the number of samples was really very, very small.
So you confirm, you believe this link exists, but the data didn't allow you to fully fully understand the relationship.
Yes, so they are not related as states say, but we should go deeper in this proof, according to me. They evaluate that qualitatively or with some parameters from the software, but again, the parameters from the software, we do not have the formula, so it's always very difficult to understand something and you don't know what's behind. This is also why we focused on transparent formulas that everybody can see and can understand easily.
Okay, thank you very much. I'm done.
Thanks for your question.
Okay, thank you. We move to the examiners with Professor Pablo Laguna from Zaragoza.
Hello, good morning. So let me start by congratulating Sara and his advisor for the work he has presented. I think it's a very comprehensive work. I would like to remark the effort made in the introductory part, both in the technical and in the physiological, which really helps to get into the business. Also, there is, it's very extensive. It goes from signal to clinical application to validation to simulation. So I think this is a remarkable piece of work. Going into questions or aspects that I would like to know your opinion and your comment, I would like to first start by a comment that has already been touched by Natasha, which is this functional rotors or functional spatiotemporal dispersion as compared to this more structural or fibrotic guided, right? So the thing is, if we accept that those situations occurs, and I am not in a position to argue a lot, but I have just read and listened to people that there exists also this functional, which means that the tissue is healthy, it's not damaged. It just occurs that because of the propagation patterns and so these things happen. So in that situation, if I well understand, the simulation that you introduced does not contemplate that situation, because in the simulations you always show healthy or with some pathology, conduction blocks, conduction delay, fibrosis, whatever. So my question is, how will you envision to extend your work in case it was considered necessary to simulate those functional issues? How do you think this can be covered in your study?
Okay, I believe that, so first, thanks for your question. I believe that concerning this part, so we started from the hypothesis. It was really the very early stage of the thesis. So we wanted to get a first idea of how things were working. This is why we opted for the simplistic assumption that the rotors are generating STD. But probably it could also be that the poor performance that we obtain when we train and we test with the synthetic data is due to the fact that we are also doing something wrong, maybe considering all the rotor pathway as related to STD. So in this case, I think we should better discuss with the experts of the Carteman's model and of the biomedical part concerning the ionic currents and all the modeling part in order to understand how it's possible to change these and accommodate the other possible hypotheses, I believe. So produce waveforms differently, for example, or create more complex dynamics.
Thank you very much. I think this is a nice aspect to consider in the future. Then other question I have is related to the peak detector issues. So when you see the signals, I mean, in the very clear case and very healthy, the peaks are clear and well defined, I will say. While when there is more fractionation, I have the impression that there are several peaks together, and I have the impression that maybe will be more adequate, but this is my question, what your opinion about this, not to concentrate in detecting a particular peak, but to concentrate in detecting like the envelope, like the peak of the envelope, which maybe is a better surrogate of the activity that is there. So, but this is a thought that I come when reading your document and listening to your presentation. So, do you think to change a bit the strategy and not to concentrate in detecting a particular peak, but detecting like the peak of the envelope, let's say, will be a better alternative, or maybe I am missing something and this is just a nonsense comment? What do you think?
No, thank you for your question. This is not a nonsense comment. Actually, it's something that we also discussed during the thesis. Our point is maybe the fact that we are not really focusing on predicting a peak with a millisecond precision. We are trying to give an indication of a possible peak that has a higher amplitude with respect to the other. Also, we use the peak to detect spatiotemporal dispersion. So we have space for some time tolerance. As you say, if we consider the envelope, this will mean, for example, we can take the maximum of the envelope or the center of the small window that we create. It shouldn't change much in the final STD definition. We haven't tested that. It would be interesting to test it. I think it would not change much in the case of the synthetic peak detection dataset. Also, actually what is interesting is that some of the ECG methods that we tested were doing something closer to that, and their performance was a bit worse. So maybe if I consider that, I mean, I'm not really sure. The best idea would be to do another simulation and check a comparison and see what happens.
That will be great. I will be curious on that. Then still in this peak detection, I try to get a clear idea what is the difference between the Pan-Tompkins classical peak detector, let's say in this repetitive ECG, whatever, and your proposal. Looking to your proposal, it seems that the really new thing is this sine type matched filter that try to match the peak styles in these signals, which in a way you may think that in the Pan-Tompkins is the square that you use when you integrate. So you change the square by the sine, trying to fit better the peaks, right? If I am right. Which can be good if you concentrate in detecting the peaks, or maybe the Pan-Tompkins is more in the idea to take the global thing. When you go to the results that you got, the comparison between your proposal and Pan-Tompkins, the numbers are quite similar, if I am right? So yes. My question is, how will you tell us, or those that will start, that is much better to use your proposal than Pan-Tompkins? So what is the real advantage of your proposals with respect to Pan-Tompkins?
In the Pan-Tompkins, first of all, thanks for your question. In the Pan-Tompkins case, we had to adapt the method to the AGMs with respect to how it was for the ECG. So there are some filtering steps. It can be computationally heavy, while our method, it's much easier. It looks almost very simplistic because we just do this convolution with the sinus that we apply only on the real data that are very noisy, but we do not apply on the synthetic one, for example. And then we will look window by window for the global maximum, putting the start of the window at the previous peak. So I believe this is better because it's easier to use. You don't have to set any filtering from the signal point of view perspective. It's already built for any AGM with any variation in amplitude. And if, for example, you compare I don't know if I put it in the thesis, but if you compare the Pan-Tompkins without the adaptation, it was not working. It was able to work just because we adapted it. So while the window method was working, it doesn't matter the data set.
Okay. Very good. So then I have a curiosity which I cannot resist to ask. In page 54, of the manuscript, equation 3.15.
1 second that I
Yeah.
take the page. 54. It's
Equation 3.15 is the second in the page.
yes.
I believe
Yes.
it should be lacking I mean, as in 3.14, which you make the ways that you look, you say are the argument which minimize something. I believe 3.15, you always meant that, right? You miss like the ways you are looking for are the argument that minimize all the thing, or not.
Yes. Yes. It's we can see 1 second. Mhm.
So
The-
I miss some part there, let's say.
Sorry, you miss?
I miss the left part of the equation, or not. Yes, that's my question.
Okay. So we have the minimization, we have the W, and we have the lambda, which is the weight that we put to the L2.
I think if I
So-
I think the question, if Pablo will correct me, is that there's the argument of the minimizer.
Exactly.
You are looking for weight, so it lacks the arg term in the equation.
It lacks the R and probably
Yes, okay, you say, yes, the arg
and
mean,
also the
yes,
W
yes.
hat equal to something. I mean, I saw it's a typo, but just for you to notice,
Yes,
and if
yes.
you have the
Thanks,
occasion to correct.
yes.
And
Thanks,
yeah, well, I mean, it's things happen, but I wanted to note it. And the last point I have is already mentioned by Ricardo, but I want to also agree with that. That is that in the publications, I miss a journal, and I strongly advise you to go for it, because otherwise things got very diluted, and that's a pity, because you will get more feedback and things it will be more spread in the scientific community. But otherwise, thank you very much and for inviting me to the dissertation, and congratulations again.
Thank you, it was a pleasure, and thanks for the nice questions.
Thank you. Next, we can move to Professor Michela Basset from Trento.
Thank you. First of all, thanks to Sara for the nice presentation and also for the nice job you did with the thesis. Congratulations to you and to your supervisor. You really cover a very wide, let's say, literature from the point of view of the physiological part, the modeling part, the signal processing, and also the artificial intelligence part. So really, it was wide and appreciated reading it a lot. So thank you very much. And yes, I appreciate a lot also the fact that you interact a lot with the cardiologist, and I think it's I know a little bit what it means. So congratulations on you also for being strong and interacting and try to obtain better data from them, and to listen to them, to listen to their questions and to the real issue they have. So I think it was really an important part of your thesis project. So I will start with a question on the database. So you work to improve the quality of the data, which are the input of all the work you have to do, no? So I look at the second database you obtain when you change the parameter setting of the CARTO system, and I saw that per patient there was a lower number of signal. If you divide the whole database for the number of patients, it's different from the first one to the second. My question was if these more stringent criteria affect, let's say, in a similar way, the mapping of the heart, or there are some areas that maybe are more affected by the fact that you restrict, I mean, the quality, because there are part of in the atrium in which it's more difficult probably to put the pentarray and to get a very good, due to anatomical reason, and have a very good contact. So I don't know if you have an idea of if you, let's say, lose a signal on the wall atria, or if there are some regions that are more penalized, let's say, because this matter, of course.
Okay, thanks for the question. It's a very interesting point, and maybe I should have added the fact that for the TPI dataset, we consider, so we acquired the TPI dataset very late, unfortunately. So it took a long time because sometimes they remember to set the TPI, they forgot stability, or vice versa, or they forgot both. Nice hospital is quite small, so they don't do catheter ablation of persistent atrial fibrillation every day. So it took a lot of time. Then another challenge has been the fact that the CARTO setting to extract the data changed completely with respect to the previous version. So it took me a long time also to understand what was in the folders. So we are going on in the timeline, and then I asked the cardiologist to label fractionation on the TPI dataset. So we were late, and I just consider a small amount with respect to the full data. So this dataset, this is not the full TPI dataset. I'm sorry, now I cannot remember the numbers of the cardinality, but disclaimer, this was a small subsample because it's the one we consider for fragmentation labeling. Also, I didn't want to take the risk to, obtain results on signals that I was not sure were correct with respect to all the changes that we had to extract them from the zip file. So I waited for the cardiologist to actually check that what I was collecting was correct, that I was putting together the right branches. So this is why it's very small due to technical issue, etc. But the TPI and stability do not restrict so much, also because we had a discussion concerning, can we be very restrictive? Should we adopt a less strong restriction? Well, we took a measure which can balance the fact that we still want to be able to see the mapping because we cannot miss relevant information, and also to be more strict not to record all the stuff that are there because we don't want the movement. And I think I was very happy. I think that we found a good threshold, and I recommend to try it, honestly, from my experience at least.
Great, thank you for your reply. Since you are on this slide, I probably misunderstood something, but the ratio between the dispersion and not dispersion sites in the TPI database, is it right? Because it doesn't, the fraction doesn't seem so.
No, you are right.
I think it's higher. It should be a little bit higher.
Yes. Yeah.
Okay, just don't worry.
Thanks.
Okay, and so I move a little bit to the simulation part. I enjoyed a lot the fact that you try to use the simulation for the validation, so try to cope with the limitation in the real data with some simulated data. I would like to ask you, in your opinion, what is the main limitation of the simulation model you use? You use a 2D tissue model, no, and with curtain mesh dynamics to calculate, let's say, or to produce synthetic electrogram. What do you think are the restrictions of your model? You don't have anatomy, or you are not able to reproduce microfibrosis, and so what do you think are the aspects that may be needed to obtain more realistic synthetic electrogram? So what do you think you miss in your simulated signals? And what's the reason?
Yeah. Thank you for your question. It's very interesting. Actually, what we miss to produce better simulation is really a degree focused on this topic, honestly, because for me, it was very hard. This is why I spent 3 months at KIT, because they were expert on that. I had to focus on the real data acquisition. I had to focus on the model development. Those softwares are not easy to be used, and also the cellular part, the physics part of the ionic mechanism was completely new for me. So I was supported in the first part by an engineer from the lab, and then from the group at KIT, which was very, very nice to me. They really fulfilled the knowledge that I was missing. So to me, in order to achieve better results on that part, what you need is really a team of people working on that, because alone it was almost impossible to get the right level. Of course, it would be more interesting to have better models, also because the problem with ours is a lack of realism. But this was what we managed to do within the 3 years, not being at all in the biomedical domain. So like I know it's not much, but I was quite happy with what I managed to achieve.
No, it's a lot. It's just if you can make a wish on some properties of the model you would like, what do you think it would be the most important features in your model to obtain more realistic electrogram? What would you do in the future to obtain more realistic electrograms?
Okay. So maybe the point where the catheter, the simulated catheter, is in contact with the tissue, we used some Gaussian method to achieve a sort of average of the cells which were in contact, and on this part I'm sure we can improve. And also really on the cellular part, we took just 3 types of cells, like healthy, scar tissue, and no conduction. So like maybe add more patterns to the tissue, also increase the type of patterns, increase the electrical range of the possible activities like rotation or not. And finally, if I could express my wish, would be use digital twins. The problem then is that we also enter computational problems. So it gets more and more difficult. The better the solution, you need to wait for a lot of time, it's heavy, but probably digital twins are the best option, where you can take, for example, real 3D mesh. We did some attempts. We haven't gone on with that, but we took a real CT scan where we applied the patches to cover the real heart with synthetic tissue, and then we tried to observe the rotation of the electrical propagation with also respect to the shape of the heart. So this would be maybe the best option.
Thank you very much. In relation with your peak detector, so you compare the properties with the adaptive Pantomsky and the nonlinear one, and they were, as Pablo also said, they were quite performing in the same way on the non-noisy data. But then you try some simulation adding noise to your signals, no? To see the robustness of your algorithm against noise, and your algorithm was very good in dealing with noise because it maintained the performance, while instead the adaptive Pantomsky has much worse performance. So I was asking, what do you think it's the added value of your algorithm with respect to the other one for in the presence of noise, because you see these different performance. So in this setting, you see differences.
So because of the filtering part and of the adaptive thresholding, the Pantomsky will be strongly affected by the signal shape, the amplitude variation, while with our method, we we are not applying a real filtering, we are not applying any band pass, so we cut off the risky part. Probably to improve the Pantomkin adaptation, we should change the parameters according to the noise level. This is why I say our method is better in real life, because you don't have to do that.
But if I understand well, your method in some way segment the signal, no? And this is based on the choice of a window that you set to the normal, to the average length of the atrial fibrillation cycle. Did you try also to see how your method is sensitive to this parameter, or do you set it worked, and that was done? And...
No. So the problem with that again is that for the real data, I don't have the ground truth for the peaks. So I cannot optimize the length of the window. I can only do some attempts and correct wrong, adjust it to the best value. This one worked well. It was coherent with respect to the atrial fibrillation cycle length, and so I decided to consider it. It would be interesting. This we started, but then we had not the time to go on, to maybe also manually label a few peaks on some real signals, and then fine-tune the window. In this case, we have a ground truth. We are able to find the optimal one. So this was the experimental qualitative optimal window for me.
Okay, so thank you. If I can suggest you, yes, to improve the robustness with respect to the peak detector, if you can have somebody, let's say, signing the right peak, so having a ground truth on the real signal, it's very important, because you know, the simulated signal are very good, but they are limited with some respect to reflect the real properties. So I think that a missing part in that chapter is really a validation in a quantitative evaluation of the method on the real signal. So I will try to go in that direction if you can convince some colleague or some cardiologist to do it. I know it's boring, but I think it will for sure improve the quality of your evaluation.
I have just maybe a small remark on that, if I can. So my original plan, as I know, it was more interesting at the moment for me to ask him the fragmentation labeling, and I could not ask to fix at the same time. My idea was like, I can compute a ground truth using the windowing approach, and then use it as a ground truth to validate a machine learning one, and vice versa, and compare. In the end, I had no time to do that, but this could be an answer to maybe to your suggestion that was in the plan, but we couldn't finish, that can avoid asking the cardiologist.
So that there can be more time in the future, maybe for accomplish also this. Just one last question, which relies on fragmentation, but on the link, of your the detection of dispersion and fragmentation. Did you try, or have you in mind to try to see the performance of your algorithm in distinguishing dispersed versus non-dispersed areas in relation with the fragmentation nature of the signal? I mean, does the performance change in the case in which fragmentation is present in the area or not? I think that having to identify peak and coupling activation, fragmentation can have a technical impact, at least, if not a physiological one. So do you think you can try to see the performance in the two settings, and what do you think about it?
Actually we choose not to include it because we agreed with Said's hypothesis that fragmentation and STD are not related. So this is why we decided not, like at the beginning there was this hypothesis. If they are related, then we incorporate fragmentation in the pipeline. If they are not related, we keep it as a side, as a separate measure. So this is why we decided to keep it separate, but if you want, it's also possible to incorporate it.
No, but I mean, just redefining your database. So you identify a category in which you have fragmented things or non-fragmented things, and inside the two bunches you find the let's say the dispersed and not dispersed, and you evaluate separately the performances just to see if the performance of your detector change in the presence of, not together with the evaluation.
Yes, I understand now. Yes,
Okay,
we can do it. Interesting. Yes, now I see it. Thank you. It's an interesting remark.
Okay, thank you.
I add it to my to-do list.
Okay, thank you. For me, it's enough. I redo the work to the chairman.
Okay, thank you. Maybe before moving to the people involved in the project, I'll ask quickly 2 questions, and then we can move to the people. So my first question is on so you focus on the spatio-temporal dispersion, and in the end, you put a lot of effort on the temporal aspects with all these algorithms to detect the peaks and find all the. And as you mentioned in the beginning, it's also a bit crude on the spatial aspect with this notion of neighboring electrons. But in the end, with these systems, we do have the 3D position of the electrodes. So do you think there could be also improvement by looking more in detail at the spatial aspects and maybe reconstructions of fronts or things that are more detailed with spatial aspect?
Okay, thank you for this question because it's very interesting, and I think this approach could have been another way to start the thesis. So we started looking at the spatio-temporal dispersion, considering the temporal aspect, because we wanted to understand the definition, and we understood that the hardest part in the definition was on the temporal. On the position, it was more or less clear that we were talking at the surrounding branches, but we have decided for this first test not to consider that. On the other hand, we could use completely different approaches. For example, we were thinking about graph theory, so to model the pentray as a graph and to consider the corresponding signal in this way. In that case, your approach would have been great, but we had to make a choice at the beginning and we opted for the other one, unfortunately.
No, come to everything in one PhD, it's already a very nice work and very nice.
So yes,
research.
we had to make some choices, but then it was really at the very beginning, so I was very new in the topic. So I tried to guide myself with my instinct to take decisions. Yeah,
as you mentioned a bit on the side, but extracting data from Carto files is in itself a huge work for those files underneath.
This was so
and getting the positions and everything
this
is also a big mess. So
yeah.
There are also technical difficulties.
Especially because we had some instructions concerning the old version of the carton. So I had from the previous PhD the extraction pipeline, but it was not working at all. Then there were typo in the lead names. It was really very difficult.
It's a big challenge. And the other aspects I was wondering is that I mean, we often consider Atrium as a surface because also the data is recorded on the surface. But even if it's very thin, it's still a volume. And in the mechanisms, I mean, of fractionation and maybe STP also, I mean, the endocardial to epicardial dissociation. I mean, there could be also mechanisms between the different layers of cells. Is it something you would consider maybe as an extension, given that you explored the simulations? Maybe simulation also could be a way to.
Exactly. So another among the many technical choices that we had to make, there was the monodomain versus bidomain approach. So we opted for the monodomain because it was easier to handle. So again, we could have decided to make things a bit harder on that side and go for like already in this model in the K81, the tissue is composed by small tetrahedra. So a little bit, exactly, we consider that, but not a real 3D mesh. So it would have been nice, but again, we had to make some choices. And we wanted to keep also, we wanted to follow at the same time the simulation path as a support, because in the end simulations are not real life, and the real data. So simulation were a bit of a support to better understand the real one, but the final focus for us were always the real data.
Okay, thank you. Congratulations again for your great work. We can move to the people involved in the project, maybe starting with Professor Axello from Karlsruhe.
Yeah, hello, and congratulations to the nice presentation of your very comprehensive work. Just a few questions. One maybe regarding the motivation and the setting of your thesis. So you use STD and fractionation to identify points that could be candidates for ablation. So now let's imagine that the cardiologist has decided to ablate at a certain point. What could happen in response to this ablation, and what would those different scenarios tell us about the arrhythmia and also the role of this point that was identified for this arrhythmia?
Okay, thanks for this question. It's actually very interesting because it allows me to better explain the fact that the cardiologists that collaborate with us will always ablate the areas related to STD, because the consensus he follows is related to the fact that you should not only ablate the area around the pulmonary vein, so it will not stop at this point, and it will continue looking for the STD and looking also for fractionation areas. In this case, what it shows is that the long-term non-recurrence of atrial fibrillation is better with respect if we do not apply this further step. But again, this is very subjective because across the different conferences that I attended, I met other cardiologists that told me, no, I only do the pulmonary veins, and then if the arrhythmia comes again, they will come at the block and we do it again, and we do a more aggressive burning the following time. So it's really subjective. In this case, they wanted to consider this, so they are the expert. We follow what they say, and this is why.
So what if we look more acutely, like this mapping is being done during ongoing ablation, let's assume, during ongoing fibrillation, let's assume. So what can happen acutely once you ablate at a specific point?
When we ablate, this part will be isolated, so there won't be any faulty electrical propagation, and so I assume that the faulty electrical activity will stop and the arrhythmia will solve itself.
But that's one scenario that could happen, that this very specific ablation point will terminate the arrhythmia. And then another one could be that nothing happens. And is there also a third option that could happen in between no effect at all and termination of the arrhythmia?
Yes, they can try for different approaches, completely different with respect to STD, or they can be more aggressive on the amount of tissue they burn if they see it doesn't stop. There are also cases where they see they're not able to stop the arrhythmia. Like I attended one intervention where the atrial remodeling was so bad and so strong that it was not possible to terminate the arrhythmia ablating pulmonary vein fractionation and STD. So it really depends from the subject. Yeah, of course, there is a limit. They cannot ablate the whole surface. They will stop at maximum the 20%.
For a specific point, I would think that a third option could be that it modulates this arrhythmia episode so that it changes the cycle length, or it terminates or converts to a different type of arrhythmia, but shows some effect. And that could tell us something also about it. And then you mentioned that it was not easy to implement those medical definitions into technical terms, so that in the concept that was put forward by the clinicians, there is a lot of human experience, a lot of mechanistic understanding probably, but not very clear in technical terms. So what would you say is the major contribution of the algorithm of the machine then? Is it to objectivize this somehow vaguely defined concept, or is there more to it?
You mean the Carto machine and their parameters, their
No, the
measurements?
algorithm to automatically annotate spatial temporal dispersion, be it in the Volta system or be it in a further developed version of your implementation.
Okay, the major limitation, so in the study about 2025 I was referring to, they stated that it was much stricter with respect to the human, so it tended to ablate more and areas that were maybe not supposed to be ablated. So this could create a bit of confusion, let's say. And the other problem is that while the cardiologists should follow a machine that tells them what to do without explaining it. So we cannot reproduce the data, we don't know which methods there are behind. All this together makes this tool unsuitable for the clinical application in the end. And this is why the centers, apart from the initial enthusiasm, now are dropping this solution.
Yeah, I think there are many limitations, as you mentioned, but one strength, I think, is really objectivizing this definition so that it's being interpreted the same way in all locations, because it's interpreted by the system and not by humans who have to work with a rather vague verbal definition. Last question is coming back to the fractionation and following up on Natasha's points. So you mentioned that fractionation can be caused by rotational activity. Which other mechanisms could underlie fractionation? Which excitation patterns in the tissue can cause fractionated electrograms?
Okay, thanks for your question. I think fractionated electrograms can also be generated by the atrial remodeling, so problems in the atrial tissue that are related to a wrong conduction from, again, a biodomain point of view, or as we said before, if it's related to the environment, so the noise, the catheter movement. I don't know if I answered your question.
Thank you. Yeah, I'll give the word back to Maxime.
Thank you.
Yes, thank you. We can move to Dr. Fabien Squara from Nice University Hospital.
Yes, can you hear me?
Yes.
Okay, thank you, Sarah, for inviting me in this jury. And I would say that it's a nice work, and you did a lot of work and effort into understanding what we do in the electrophysiology laboratory, and it was nice working with you and collaborating. So I hope that we can continue it. Just to be clear, there is a still ongoing debate on what has to be done for persistent atrial fibrillation. So what is established is that we have to isolate pulmonary vein, but other lesions really depends on the team. So we are not sure if it's better to perform tailored ablation or if it's better to perform linear ablation. And what we know is that if we perform tailored ablation, we have less atrial fibrillation in the follow-up, but we have more organized atrial arrhythmias. So most of the time, you cure one arrhythmia, but you create another arrhythmia. So that's why a lot of people, a lot of electrophysiologists that were doing STD ablation are slowly switching to linear ablation, actually. So I had, as a cardiologist, a question regarding the clinical use of your pipeline. You already spoke a little bit about it. But what will be nice is not to do like the Volta system. I know it's not the same method, but it's not giving us just a yes or no, like a binary result, but a continuous measure. So it will be nice to have a continuous result so that we can continue the research and see if we can discriminate using your continuous measures, like the degree of fractionations or the number of rotations in the STD, if we can discriminate the functional and not the functional, so the clinical zones that we have to ablate using the termination of the arrhythmia or maybe the complexity of the atrial fibrillation that can decrease after ablation of this zone. So it's only a comment. I have one question though. Every few months we have new catheters coming. So how easy will it be to translate your pipeline to another catheter? Because we use the Pantarray, but we also use the Octarray, we use the Optral, we use the Farapulse. So on a daily basis, we can use probably 5 or 6 different diagnostic catheters. And if you used the deep learning, it would be very complicated, I guess, because you had to create a new data set. And so I understood that with your system, it will be much easier to translate it.
Yes. I believe it would be easy because you can simply change the group of comparison part. The big part is computed lead by lead, so it will not change. And then the other part that you will change are, if it's the case, the criteria on the time shift to classify STD and non-STD. So it's just a matter of building different group of comparison among adjacent leads. Then, as we said, the pipeline is composed by different blocks. So you do not have to train anything. You can just test it on the new data that you have. So it's very simple to adapt it.
Okay, and how easy will it be to implement it to the CARTO system or to the electrophysiology recording system? I know we have to continue the work and confirm that it's working, but will it be easy to implement it in the CARTO system? Because I doubt it. It's quite a closed system, and I don't know if we can implement a new algorithm like that.
So online, I don't know, we should discuss with CARTO people because I'm not sure you can access the computation. Offline, we can compute after the evaluation has been performed. So it depends. For the real time, we need to discuss with them. It depends from the CARTO, how close it is.
Okay. I have no further questions. Thank you.
Okay.
Thanks for your questions.
And we conclude with Vicente.
Thank you, Maxime. Well, first of all, I would like to thank all the jury members who accepted to be here today to evaluate Sara's work. I know you are very busy people, and so I really appreciate your being there. In particular, of course, to Natasha and Ricardo for their careful reading and reporting on the manuscript. Given that the manuscript it wasn't just a short story. I think it was about 250 pages long. So well done. I appreciate that. I also, of course, I would like to congratulate, to say a big thank you to Axel, because he contributed in a significant way to Sara's thesis by welcoming her in Karlsruhe for 3 months last year. And I think that included that helped her to add this simulation part, which is, I think, is a very enriching addition to the thesis. And so thank you very much, Axel. And also that allows us to to continue working in we have a new ANR project where Axel is also a partner. So I think that's also a very nice thing to do during the thesis. And of course, also thank you to Fabien for his patience and his never-ending support with Sara's work. I think I really appreciate his availability, because I know I was witnessing that. They were interacting almost every 2 weeks. They had very frequent video, almost the time were video calls, but also sometimes Sara went to the hospital, and so thank you. I think I was very, I was just bring capital to Sara's thesis. So a big thank you to you all. And also thank you, Maxime, for chairing the jury, even though there wasn't many options. So I would like to just also to general comment to Sara. I'm not going to ask any question, obviously. As we mentioned during the answer the question and answer session, we should keep in mind the history of the thesis. This is a very applied, very focused on topic, focused on biomedical and specifically on cardiac analysis, cardiac analysis. You come from a rather theoretical, you have a diplomas on applied mathematics, machine learning, and so for you was a big shift of focus on a completely topic was absolutely unknown to you before you came, and you got very quickly familiar with the topic, with interacting with cardiologists, exporting data, and things that you hadn't done before. And I think this is something to be taken into account also in your what you did in your thesis. I also appreciated your perseverance, Sara, because it's true that you went through very difficult moments, especially as we saw in the presentation, with the data. Data, certainly, your thesis is a very good illustration that in artificial intelligence, sophisticated algorithms and computer power is not the main part. The main part is actually data, as you mentioned, because if your data are wrong or your data are poor and are not representative of the problem you want to solve, everything you want to do next would be probably wrong. So I think you illustrated very well this, and you show a lot of energy and enthusiasm to try to go around these difficulties. This is why also you wanted to go to Karlsruhe. We tried to develop the computational part or the simulation part. You also were very motivated to attend conferences and summer schools. I had sometimes this Italian force that comes, this energy. I had to channel it a bit, because otherwise there was a risk of dispersion, but I think we managed to keep it in the right track. And as it was mentioned also by some of the jury members, the only downside to me, the downside in your thesis is the lack of journal publications, but I hope in the remaining weeks or months we'll be able to submit 1 or 2 papers with the main results. Okay, so it's true that there is still, but this is an initial work. It's still a lot of practical things to do to make the results clinically applicable. But I think your work is a good stepping stone to get to this clinical impact and clinical application. So I wish you all the best for the continuation of your career, and I hope we can still keep in touch, at least during the writing of the journal manuscript that we still have to send. But I'm not going to make any comment on the questions. I think you answered quite convincingly to most of the questions that were asked, the many questions. As Natasha and other jury members mentioned, there is we didn't have the time to look at the link between STD and the kind of mechanism, whether functional or pathological. This is actually something we didn't have the data to do so, and it's something we could do maybe in a further work with in cooperation with colleagues doing computational cardiac modeling, because there's certainly a modeling part to be taken into account there. Also, the main hypothesis was actually the rotors. This is the hypothesis that was mentioned in Seth's work in 2017. We didn't check whether STD could be caused by other mechanisms. And again, maybe we'll need some, to get some insight into that, we'll need some good computational models to try to see whether STDs can come from other phenomena. And well, this is everything I wanted to say. Well done, Sara, congratulations. And I'm very glad that you had this motivation to finish your thesis before the 3 years, and you did 3 years minus 2 weeks. So I think you're in the you achieved your goals. Well done.
Thanks.
Okay, thank you. So we'll move on to the deliberation. I don't know. Mistake here.
The only thing is that people, the audience will have to go.
I will
Sara
stop the YouTube stream.
You can just you can just cut your. I'm co-host of the room.
I can leave the room and cut the.
You can, yeah, I'm a co-host. I can leave the room.
So if I close, it will be closed only for me.
Yeah, because I'm co-host. So try to.
No,
Try to close the. Yeah, I'm the host now. Yeah, so it's fine. Okay.
Thank you. Can I?
Another thing is I need to make sure that YouTube. How do we stop the YouTube streaming?
Yes, I can.
Is there anything to
Yes.
program we can do? And just stop it.
No,
Here.